Hi, I'm Samir. I'm excited to present Falcon, which is a framework for privacy preserving machine learning. This is joint work with Shruti, Fabrice, Eyal, Pratik, and Tal. The focus of our MPC framework is on machine learning applications. Similar to prior works, when we take a machine learning model such as this and want to do either private training or inference on it, we break it down into a bunch of functionalities and come up with secure computation protocols for each of this. So the three biggest takeaways of Falcon are first, we extend this, we operate with security against both semi-honest as well as malicious adversaries. So in the honest majority corruption model, and so one party can be corrupt both semi-honest or maliciously. The second key takeaway of Falcon is that protocols are extremely simple, so that makes them very easy to implement as well as highly performant, so they don't rely on any heavy cryptography. And then the final key takeaway is we evaluate over very large networks and datasets such as AlexNet VGG16, which contain hundreds of millions of parameters, also on larger datasets. And we do a number of other experiments to really give some new insights on this domain of privacy preserving machine learning. So I'm going to present each of these three takeaways like what we do in the reverse fashion. So I'll start with malicious adversaries. So our starting point is sort of the secure NN protocol, which proposed a three-party computation model with three parties, but then underneath it used a 2 out of 2 secret sharing. So there were two primary parties which would actually perform the computation and a third helper party which would help them out. A consequence of a 2 out of 2 secret sharing is that whenever you reconstruct a value, for instance, the secret A, which is as shares A0 and A1, each party just sends their share to the other party and both of them now have the value of the secret A. But this has no security against a malicious adversary. So if one of the parties is corrupt, then they can arbitrarily lie about their value. And so you don't get any correctness of computation guarantees when dealing in such a model. The way we address this issue is using something known as a 2 out of 3 secret sharing. This allows you to have, it's also known as replicated secret sharing. So each party, so the secret A is actually split into 3 different shares, A0, A1, A2. And each of these shares, 2 out of these shares are given to each party. So each party is missing one component out of these shares. One consequence of this, in the semi-honest model, you could just give each party their missing component. And so, for instance, the leftmost party can actually receive the value A0 from one of the other two parties and actually reconstruct the value A. But also in a malicious setting, like the intuition is that you could actually do the reconstruction two ways. So you have robustness in the sense that the value A0 is held by two other parties. And so if both of them send a value and if the value received are the same, that gives you a guarantee that there was no malicious behavior, because in particular, when you have a three-party model with a single corruption, we know at least one of the other two parties is honest, since there are two honest parties. And this allows you to do a maliciously secure protocol with this one corruption model. So that's sort of the first takeaway, that you can achieve malicious security using this replicated secret sharing as the foundation of the entire protocols. The second key insight is this is the functional dependence of secure NN, but that's largely the case for most prior work. So each of these works usually would use like roughly a similar functional dependence. So in particular, we have these set of functionalities such as max pool, ReLU, division, matrix multiplication. All of these are common to pretty much all these prior works, because the end goal is to actually train neural networks. Secure NN had this set of protocols which they proposed, which was a private comparison protocol, compute MSB, and share convert. And the share convert and compute MSB, these were really the core contributions which actually allow you to do a derivative of ReLU or a comparison. And each of them use the subroutine private compare roughly once. And private compare is really the bottleneck of these protocols. And so the overhead of this is roughly 2 times the overhead of a private comparison protocol. So the first biggest change Falcon makes is in actually replacing these two functionalities with a single functionality called wrap, the intuition for which I'm going to present a little later. We replace it by that, so that immediately improves the performance by twice. And So as a consequence, the first thing is we actually enable such a protocol for this in the replicated secret sharing model, whereas SecureN was a highly two-party computation model, so it was really using the third party uh, to actually do very to do simple things which cannot be proven secure in the maliciously secure model. Whereas the first contribution here is to actually enable a protocol for RAP, which is secure even in this replicated secret sharing. The other one is the highly efficient part is the protocol for this actually does not use any heavy crypto. It's just addition, subtraction, bit operations, and not even secret bit operations over local values. And so that makes it highly performant. And then the final change is we actually implement a leaky version of a batch norm protocol. So where it reveals a quantified amount of information, but we have a very efficient with concrete efficiency, we have a very efficient protocol for batch norm, which is really required for training large networks such as AlexNet and PGG. And these are really high multi-million parameter networks, so such as this. So that's what can largely be said is how we change the functionality dependence. So before I proceed, let me give a quick intuition. Before I set up the intuition behind the comparison protocol, I'll also talk briefly about the fixed point arithmetic part of this. So when we want to train over neural networks, we actually want to use floating point values. And on the other end, when we want to do cryptographic operations, we prefer using fixed point values. And so if this is the range of values, so this is 64-bit values, and this is the unsigned 64-bit integers and data type we are most familiar with. So zeros represents, all zeros represent the number 0, and all 1 represents the number 2 to the power 64 minus 1. Fixed point arithmetic implies that we actually we interpret these values differently. So we actually consider there is a binary point somewhere. So here it's shown at the end from 5 decimal digits. And so the fixed point precision of this is 5 binary bits. And so a number such as a unsigned 64-bit number, which is 7, which is shown in here, is actually represented by the floating point number, which is 7 over 32. And 32 is the 5th power of 2. And so this is sort of the mapping which the protocols have to kind of implicitly take into account, that there is a fixed point encoding in there, and then consider them. So when we talk about this sort of encoding, the first thing is positive and negative numbers are encoded in these two half ranges. And so the ReLU, or the comparison function, is really just figuring out if a number is positive or negative, and so we want to find if a number is in the first half or the second half. So that's the foundation. So let's take a look at what the secure comparison problem is. So secure comparison on the left is we have the input A, which is secret shared as A0, A1, A2. And as I mentioned before, it's replicated secret sharing. And so each component is shared, is held by two parties. And on the right, we have the output, which is, let's say, the most significant bit of A, because most significant bit, as we saw, is indicates whether you're in the left half or the right half. And so if you want to compute this, so let's say that most significant bit is X, which is 0 or 1. We have shares of X, let's say, in the arithmetic sharing here. So the way we approach this is we break down this into a few different components. So the first insight is that once you have arithmetic secret sharing A, you can only have one of three possibilities, that the summation A0, A1, A2, that is actually in a modular arithmetic sense is always equal to A, but it can take one of three values. It can be between 0 and 2 to the power k, which is the modulus here. So that's the first possibility. The second one is it's actually between 2 to the power k and twice that value. And the third one is between twice and thrice the value. So those are the only three possibilities, because each individual share is a number between 0 and 2 to the power k. And so when you add three of them, the sum can at most be 3 times 2 to the power k. And so once we have these three possibilities, we define something called as the RAP function, which basically says that whether you are in possibility 1, 2, or 3. And the biggest insight here is that this function is sufficient, or like just knowing this A0, like whether we are in case 1, 2, or 3, that functionality is sufficient to actually compute this MSB. And that insight is given by this equation. What it says is the most significant bit of a number is actually a local operation. So once you compute this wrap function on three different values, and these different values are just twice the value of the shares, you can actually compute the MSB using local operations. So you compute this wrap function and then you XOR it with MSBs of A1, A2, A3, which are actually already locally available to each of the parties. And so that's the insight. Let's take a quick look into why, some intuition behind this insight. And so this the best way to look at this is as going the old school way of like writing this addition. So let's say A0, A1, A2 are these three numbers, and then they add up to this, in a modular sense, add up to A, and so this is the sum. Now, when we say we are interested in computing the most significant bit, we are interested in this bit 0 here. The way this bit is done as in terms of the addition is simply going to be the sum of this bit, this bit, this bit, like the MSBs of A0, A1, A2. And it's also going to contain one more factor, which is what is the carryover. And that's really the insight, that noting that the carryover of this remaining half is simply the wrap function computed on twice the values. And the reason why it's twice the values is because once you compute 2 times A0, it just bit shifts this entire box by one bit to the left. And so that gives you the carry bit of this operation. And then effectively, if you XOR that along with the MSBs of A0, A1, A2, you get the MSB of A. One detail which I missed here is even though RAP3 has 3 different possibilities, so it can take values 0, 1, 2, we only consider the mod 2 reduction of that, and so all you care about is the carryover 0 or 1, and so that's effectively what we do in the paper. So with that, I'm going to jump into the experimental evaluation components of this work. So Falcon is open sourced and it's available at this repository. It has passed the artifact submission, and we are happy to have people use this code base. Falcon, the pseudocode is really simple. Once you write some of the basic functionalities as addition, subtractions, you can actually write it in a few lines of code. And so that's one of the benefits of a simple protocol. The second one is we actually evaluated over a series of different neural network architectures. So we go from all the way from simple multi-layer perceptrons such as secure ML, which the values in these boxes are the number of parameters these networks use, to some CNN such as Mini and Lenet, and then all the way to large networks such as AlexNet VGG16. So these contain more than tens of or hundreds of millions of parameters. So the first work is comparison with prior work. And so here, this is numbers presented. So we perform extensive comparison with prior work on the same set of networks. We also test our networks over LAN as well as WAN. And so as you can see here, like Falcon generally outperforms prior work by a significant margin. The communication is also significantly lower. We also perform experiments for private training. So here are some of the frameworks which do private training. And then again, we benchmark these over both LAN and WAN network settings. The other set of experiments is we actually run experiments on larger networks. So here we run it on AlexNet VG16, on CFAR, as well as like tiny ImageNet datasets. And these are the benchmarks of the protocol. Some of these results are slightly grim in the sense the time taken to actually train these networks can run all the way up to years. But once again, like the protocol, the code base is not highly optimized in that sense. And so there is definitely room for improvement here and getting these training times down to more practical values. The one other really interesting insight when running the benchmarking over larger networks is presented in this graph. So this is something which came as a slight surprise. Partly also it has to do a lot with like how this the program is implemented and over what frameworks and. But each different MPC protocol, like so if we take a functionality such as convolution, matrix multiplication, comparison, and so on, all of them have different scalings with sizes. And so if we take different network architectures, they scale very differently in MPC as the size grows. And what happens is once we go to very large networks, the matrix multiplication cost just starts dominating, which in hindsight starts making sense because matrix multiplication is a super quadratic operation. And so no matter what happens, the computation is going to go more than quadratic. Whereas the the rest of the protocols, comparison, which is the most dominant cost from the MPC point of view, still runs over vectors or vectors over which are at most quadratic in the size of the matrices. And so that tussle eventually starts blowing up when you go to larger networks. And so these start becoming more and more compute dominated. So here is a graph which presents the relative overhead of a network time spent in communication versus in computation. So this is also a very interesting insight that it challenges our understanding that MPC is just always communication bound. It really depends on the setup, and it can become compute bound when you go to very, very large networks. We also provide some comparison with plain text computation. So these are not apples to apples comparison because the plain text versions are run both on CPU as well as GPU, whereas the MPC versions are only run on CPU. The other difference of comparison is that they are run over PyTorch, which is really the popular benchmarking framework. And it generally shows that like over LAN, MPC protocols are about 2 to 3 orders of magnitude slower. And the WAN setting could be another order of magnitude slower than that. And this is benchmarked only for the larger networks. Finally, we also find out that if you're only focusing on private inference, 32-bit values do give us like sufficiently high precision. And so this is verified in this experiment here. So on the left, we have a clear text output on the same network. So done with no privacy in it, and it's over 64-bit float, so it has arbitrarily high precision. And on the right, we have the MPC output of private inference performed using Falcon over only 32-bit integer data types. And as you can see, the values usually agree up to 2 or 3 decimal digits. And this is already huge because neural networks already are fairly robust. And when we actually perform this accuracy test much more highly, here we have experiments which show the training and inference accuracy of the plain text network, but then also we can see the inference accuracy of Falcon when we do it privately. And for most networks, the accuracy does not change at all because it's just so robust. So even though each individual value is slightly different between them, the overall prediction result doesn't change. And that is quantified by this other term, which is the relative error. So once we pass it through the entire network, the final values have a very low relative error compared to the plain text values. So this sort of quantifies like how error propagates through the entire network and how different the values are because of the approximation in MPC. So with that, I would like to thank you for your attention and happy to take questions. Here is the Falcon repository once again and the link to the paper on arXiv. Thank you.